Okay, this is like my fourth video in a row tonight. Let's see if I can get through it. I'm already feeling a little kind of, you know, dead. So hopefully, uh, hopefully we can make this work. We're doing some polar integration, and there are a lot of these questions, and some of them are kind of bad, especially like this first one. This is one of the more difficult polar integration questions, and these come in. The way I make these PDFs, they're in a random order. So, this is the one that we're stuck with. So we see that we're integrating over the region in the first quadrant enclosed by the circle of radius 2. So that would be that entire area over there, but I really shouldn't have drawn that because if we take a look at our other things, we're bounded by the line y equals 0 and the line y equals x. So we're actually dealing with half of that, which is this area here. And we know that we can set that up in terms of polar coordinates, r, dr, d theta, with r running between 0 and 2, and theta running between 0 and pi over 4. And then we see that our integrand is going to be 2x squared, which is 2r squared cosine squared theta. And we can stick this r over here, and we're ready to integrate. So let's not think about our cosine squared theta. We'll just remember that we've got to integrate it over here, but let's deal with this r. So integrating, we're going to get r to the fourth over 2 on 0 to 2. This is going to be 8. And so we are left with an integral from 0 to pi over 4 of 8 cosine squared theta d theta. And noting up here that we're given this nice little hint of an identity to use, we can replace this integrand with the integral from 0 to pi over 4 of 4 plus 4 cosine 2 theta d theta. Integrating, we'll get 4 theta plus 2 sine 2 theta on 0 to pi over 4. And let's see what this evaluates to. This will be pi plus 2 sine of pi over 2. Well, that's just going to be plus 2. And down here, we will get 0 plus the sine of 0, which is 0. And so pi plus 2 is our answer. Which of these integrals is going to represent the volume of a solid under this guy and above that guy? Okay, so this is an interesting, it's a very weird question here because the answer choices that they're giving us are in polar coordinates, but we notice that up here we would have to use cylindrical coordinates to make this entire thing work. So really what we're doing is setting up a cylindrical integral that turns into a polar integral later on down the line. So even though this is the polar integral playlist, I actually didn't know that I messed up and put an integral that's really a cylindrical integral on here until right now. So I'm kind of feeling, I'm kind of annoyed, but I guess we can do this now. So setting this up in cylindrical coordinates, we see that, well, this is just a cone. And we're under that cone and above the circle in the xy plane of radius 7. So dz dr d theta, we can set up these bounds. Looks like z is going to run from 0 because we're looking at the xy plane over here. And it's going to be bounded on the top by r squared. Because we know our conversion is x squared plus y squared equals r squared. Okay, great. Oh, sorry, I called that thing a cone. It's not a cone. It's a circular paraboloid, or an elliptic paraboloid. The tests have called it different things over time. Yeah. Whoops. Yeah. No. This is what I'm talking about. It's kind of doing too much math at once. That is most definitely not a cone. Okay. Our bounds on R. Well, we're above this region, and as it turns out, that'll just give us our bounds. This is kind of you can think of this as the maximum size of the shadow that this thing can have. Because if we graph this thing, we're going to have this circular paraboloid opening up here, and it only stops opening up when it gets to a radius of 7, because we're bounded on the bottom by that thing, and that's kind of cutting it off up here. So we're looking at this volume in here, and so r is going to run from 0 to 7, and theta, well, we want the whole thing, so from 0 to pi, 2 pi. And okay, so we see that we have no z's in here. We're just integrating 1 dz, so that's just going to multiply this r squared in. So we are left with this thing, which should match one of our answer choices. So we can get rid of anything with a 49 up here. And we can get rid of this because it has an r squared. We're looking for an r cubed, and there's our answer. Super weird question. Should have kind of just skipped it. And I do need to write down this one because otherwise I will forget to put it in the cylindrical integration compilation, Okay, let R be the region in the first quadrant between this line, and inside this circle, and we're evaluating that whole thing right there. So let's draw this out. We're just in 2D. We're looking at the line y equals 0, the line y equals root 3x. So that's going to be something like that because root 3 is greater than 1. So y equals root 3x, and the circle of radius 2. So there's our region right here. And now we really do want to figure out what this angle theta is, because right now we don't know. We're given this weird kind of thing up here, and sadly, I never learned what the I think it's you just take the I know tangent's involved, an inverse tangent is involved, but what I do know is that we can kind of think of it in another way. So we see that for every unit x that we go over, so 1 unit x, we're going to go up root 3 units. And if we make a triangle out of this, we're going to see that our hypotenuse is of radius 2, which makes sense. Let's take this down to the unit circle. Let's divide everyone by 2. We can do that because it'll just be a similar triangle. 1/2. And now this is something that we recognize from our unit circle. And we know that when sine is root 3 over 2 and cosine is 1/2, that our angle here is pi over 3. And so that's kind of how I think through it. It feels more safe, more stable than using some formula, which I'm sure is very easy to use. I'm extremely weird about this kind of thing. So now we can set up our integral. We want to integrate xy, so that's going to make our entire integral r cubed cosine theta sine theta dr d theta. Theta runs from 0 to pi over 3, and r runs from 0 to 2. So yet again, we're just going to deal with, and I need some more space. We're going to deal with our r first. So r to the 4th over 4 on 0 to 2, that's just going to give us 4. So now we're left with the integral from 0 to pi. That's not a pi. The integral from 0 to pi over 3 of 4 cosine theta sine theta d theta. Well, one of our identities that they like to make us use a lot is the identity that says that 2 cosine theta, that cosine theta, that 2 cosine theta sine theta is equal to sine 2 theta. So we can replace this thing, the integral from 0 to pi over 3 of 2 sine 2 theta d theta, which when we integrate will give us negative cosine 2 theta evaluated on 0 to pi over 3. Well, the cosine of 2 pi over 3 is going to be negative 1/2, and combining that with the negative that we already have out here, that's going to give us 1/2. And then over here, the negative cosine of 0 is going to be negative 1, so our answer is 3/2. Let's evaluate this bad boy using polar coordinates, and pretty much all that we have to do is set this thing up. We see that y is bounded on the bottom by the line y equals x, and bounded on the top by the hemisphere of radius 1. So we'll put that whole thing in there, but we also know, looking at our bounds on x, that x runs from x is equal to 0 to x is equal to root 2 over 2. And it's going to drill into your head that 1 over root 2 is root 2 over 2. I've overheard many conversations of people complaining about how they missed a question on midterm 2 because they didn't put 2 and 2 together in the moment, that 1 over root 2 is in fact root 2 over 2. And so there's our region, and we see that this integrand is just going to turn into 3r. So we can set this up as an integral r dr d theta, where r runs from 0 to 1, and theta runs from pi over 4 to pi over 2. And finally, our integrand, we said, is going to be 3r. We can combine. Okay, so integrating r cubed on 0 to 1 is just going to give us 1. So we can get rid of all this. And we're doing this sad looking integral here, which is just going to give us pi over 4. Let's evaluate this guy by converting to polar coordinates. Same kind of thing. We got to graph this thing out. We're bounded on the bottom by y equals x, and on the top by the hemisphere of radius 2, and then x is running between 0 and root 2. And note, if we were to do this with the unit circle, this would make a little bit more sense, because root 2 over 2, if you make that circle of radius 2 instead of radius 1, well, we're going to multiply our x value by 2. And so instead of integrating up here like we had the hemisphere of radius 1 and 1 over root 2, which is root 2 over 2, over here we have the hemisphere of radius 2 and root 2 not over 2. And so there's our region. Here's our region that we're dealing with, pretty standard. And our integrand is going to become r squared. So overall, we're integrating from pi over 4 to pi over 2, and from 0 to 2 of r cubed dr d theta. Well, that's r to the 4th over 4 on 0 to 2, which is 4. And so get rid of all this, replace it with a 4, and then all this integral is going to do is multiply by the difference here, which is pi over 4 times 4, which is pi. Let's evaluate this double integral where d is the region bounded by the x-axis and the curve, the hemisphere of radius 1. So we're bounded by the x-axis, so our hemisphere is going to be this whole upper hemisphere of radius 1 everywhere. And all we have to do now, because we know that our bounds on integration are going to be 0 to 1 r dr, 0 to pi d theta, all we have to do is convert our integrand, which is going to be 2 e to the r squared, which is perfect because we can do some u sub with the r that comes with our dr. And we will see that integrating this dr is going to give us the integral from 0 to pi times the quantity e to the r squared on 0 to 1, which will give us e and 1. So this whole thing will simplify down to e minus 1 d theta, which is going to be pi times e minus 1. Oh my god. Okay, so this one I actually did catch, and I hope you can see it right away too. This is another not so polar integral. This is a completely cylindrical integral. And that's what I'm not going to do because I did catch this one and I didn't think I had it in the set of screenshots that I was turning into a PDF. So apologies for that, but that's also great because it means we only have 2 questions left to do. Okay, right off the bat, this integrand is looking very scary, but our bounds on integration are looking very fine because we see that since we're in the first quadrant, our bounds on theta are going to be 0 to pi over 2. And since we're between these circles, our bounds on r are going to be between 1 and 2. But this whole integrand business is looking scary. So if we convert this, we know that x is r cosine theta and that y is r sine theta. So this will be r cubed cosine squared theta sine theta over r squared to the 3 halves, so r cubed. And okay, it's actually not so bad. So we've got this thing, and we can stick it right in here with our r and integrate away. So r squared over 2 on 1 to 2 is going to give us 2 and 1/2, so we get 3 halves multiplied by the integral from 0 to pi over 2 of not cosine with not cosine with 2 O's, cosine squared theta sine theta d theta. And if you're out of practice, this might still look scary, but we know that we can just use some u sub. We can set u equal to cosine of theta. Du is equal to negative sine of theta d theta. So this whole integral becomes not pi, I meant 3 over 2 times, oh sorry, we need to switch our bounds on integration around. Since u is equal to cosine of theta, this will be 1, this will be 0, negative u squared du. And we know that we can flip our bounds on integration and negate all of our terms. So this will be 0 to 1, and flipping that sign. So we can evaluate this. This will be, oh my god, my math is going down the drain. 3 over 2 times the quantity u cubed over 3 on 0 to 1, which is just going to be 1/3. So 1/3 times 3 halves is just 1/2. Let's compute this dude. All we have to do is convert to polar coordinates. We see. Let's see if we can practice doing this without a graph, even though it's not even good. It's not even a good skill to have for the exam, really, because graphing things out is always your friend. But we see that, y is bounded on top by the hemisphere of radius 3, and x runs from 0 to 3. And so, kind of picturing that, if you can, we're going to have the whole first quadrant and nothing else. So r runs from 0 to 3, r dr, and theta runs from 0 to pi over 2. And our integrand is going to be root 9 minus r squared. And I like moving the r's in front. Okay, so integrating, we're going to get 1/3 9 minus r squared to the 3 halves, evaluated on 0 to 3. This will give us, let's see, 9 to the 3 halves, which is 27 over 3. And over here, we're going to get 0. So, there we go. Sorry, 1/3. Negative 1/3. It's a negative sign in here. So negative 27 over 3. So we get 27 over 3 multiplied by pi over 2 because we don't have any thetas to integrate over. And we are going to get 27 pi over 6, which is the same thing as, let's divide everything by 3, 9 pi over 2. And we're done. Okay, hopefully this was helpful. Let me know if any of these were wrong, and I'll do my best to make sure that the cylindrical integrals I included by accident actually make it into the cylindrical integration compilation. Maybe I should make a compilation of all the integration. It will be like, I don't know, 4 hours long. Um, yeah. Okay. Thanks for tuning in.